Download this code from codegive.com, link in the description below. OK, let's dive deep into the differences between stack and heap memory in Java. This is a fundamental concept for understanding how Java programs manage memory and is crucial for writing efficient and bug-free code. Understanding memory management in Java. Java, unlike languages like C or C++, provides automatic memory management. This means you, as the programmer, don't explicitly allocate or deallocate memory using functions like malloc and free. Java's garbage collector, GC, handles this automatically. However, understanding where objects and data are stored is vital. Java uses two primary memory areas for this, the stack and the heap. 1. Stack memory. What it is. The stack is a memory region that operates on the last in, first out, LIFO, principle. Think of it like a stack of plates, the last plate you put on is the first one you take off. Purpose. The stack is primarily used for storing local variables. Variables declared within a method, not instance variables of a class, are stored on the stack. Storing method calls and execution context. When a method is called, a stack frame is created on the stack. This frame contains the method's local variables, parameters, and the return address, where the program should return after the method completes. Managing method execution flow. The stack tracks the order of method calls and ensures that methods return in the correct order. Characteristics. Fixed size. The size of the stack is typically fixed and relatively small. You can usually adjust it through JVM parameters, but there's a limit. Fast allocation / deallocation. Memory allocation and deallocation on the stack are very fast. This is because the stack pointer simply needs to be moved to allocate or deallocate memory. It's a simple, predictable operation. Automatically managed. Memory is automatically allocated when a method is called and automatically deallocated when the method returns. Thread specific. Each thread in a Java program has its own separate stack. This means local variables are thread safe by default. Limited lifetime. Data stored on the stack has a limited lifetime, existing only as long as the method in which it was created is executing. Stack overflow error. If the stack becomes full, example due to infinite recursion, a stack overflow error is thrown. 2. Heap memory. What it is. The heap is a large memory region used for dynamic memory allocation. It's a much larger memory pool than the stack. Purpose. The heap is primarily used for storing objects. All objects in Java, instances of classes, are stored on the heap, regardless of where they are created. Storing instance variables. Instance variables, fields, of a class that are associated with an object are stored on the heap as part of the object. Dynamic data. Data that needs to persist longer than the execution of a single method. Characteristics. Dynamic size. The size of the heap can grow or shrink at runtime, depending on the application's needs. Slower allocation / deallocation. Memory allocation and deallocation on the heap are slower than on the stack. The JVM has to search for available memory blocks and manage fragmentation. Garbage collection. Memory on the heap is managed by the garbage collector. The GC automatically reclaims memory occupied by objects that are no longer reachable, not referenced by any live part of the program. Shared across threads. The heap is shared by all threads in a Java application. This means that access to objects on the heap must be synchronized properly to prevent race conditions, multiple threads trying to modify the same object simultaneously. Longer lifetime objects on the heap can exist for the entire duration of the application, or until they become unreachable and are garbage collected. Out of memory error. If the heap becomes full and the garbage collector cannot free up enough memory, an out of memory error is thrown. Key differences summarized in a table. Feature: stack memory, heap memory. Purpose: local variables, method calls, execution objects, instance variables, dynamic data. Size: fixed, relatively small. Dynamic, can be large. Allocation / deallocation: fast, automatic. Slower, garbage collection required. Management LIFO: garbage collection. Thread safety: thread specific, local variables are safe, shared across threads, requires synchronization. Lifetime: short, limited to method execution. Longer, until garbage collected. Error: stack overflow error, out of memory error. Code example to illustrate stack and heap. Explanation of the code example. 1. Memory example class *. This class has an instance variable. Instance variables are associated with objects, so they reside in the heap. 2. Calculate sum method *. A and B are method parameters, which are treated as local variables. Sum is a local variable declared within the method. All these local variables, A, B, and sum, are stored on the stack when the method is called. They are removed from the stack when the method returns. 3. Main method *. Local var1 and local var2 are local variables, stored on the stack. Obj1 and obj2 are reference variables. A reference is essentially a pointer to the memory location where the actual object is stored. The reference variables, obj1, obj2, are stored on the stack. The objects themselves, new memory example, 5, and new memory example, 15, are stored on the heap. Result is a local variable, stored on the stack. Important considerations. Garbage collection. The garbage collector is a background process that periodically scans the heap to identify objects that are no longer reachable. When it finds such objects, it reclaims the memory they occupy. This prevents memory leaks. Synchronization. Because the heap is shared across threads, you must use synchronization mechanisms, example synchronized blocks, locks, to protect objects from concurrent access if multiple threads might modify them. Failing to do so can lead to data corruption and unpredictable behavior. Mutability. The stack primarily contains primitive types and references, which are often immutable, unchanging. Objects on the heap can be mutable, their state can be changed. This difference affects how you reason about data and program behavior. Example demonstrating potential for out-of-memory error and stack overflow error. Explanation of error examples. 1. Out-of-memory error example. This method continuously adds 1 megabyte byte arrays to a list. Eventually, the heap memory will be exhausted, and the JVM will throw an out-of-memory error. The try-catch block catches the error and prints a message. 2. Stack overflow error example. This method calls itself recursively without a base case, a condition that stops the recursion. Each recursive call adds a new frame to the stack. The stack has a limited size, so eventually, the stack will overflow, and the JVM will throw a stack overflow error. The try-catch block catches the error and prints a message. In conclusion, understanding the differences between stack and heap memory is crucial for writing efficient and robust Java programs. Knowing where objects and data are stored, how memory is managed, and the potential for errors like out-of-memory error and Stack Overflow error will help you write better code, diagnose problems more effectively, and optimize your applications for performance. Good luck.